Hey guys, this is Bill. Welcome to another session of R with me. In this video, I'm going to teach you how to do lasso and ridge regression in Rstudio, and more importantly, how to do a cross-validation with these two types of regression methods. If you would like to run the code by yourself, you can use the link in the description to download the R script and run the code on your own. This can be really helpful if you want to write the code by yourself in the future. Without further ado, let's get into the code. The first line is to set seed such that you can get the same result as I do in this video. Second line imports the library mass, which contains the dataset that we are going to use in this tutorial video. The dataset's name is Boston. You can key in $Boston in the console in order to know more about the dataset. Basically, the Boston dataset tells us about the values of houses in different suburbs of Boston. It contains 506 observations and 14 features. The last column, or the last feature, is the y variable. So we have 13 independent variables, or x variables. I store the number of rows and number of columns in variables n and p respectively. I also import the glmnet library, which does lasso and ridge regression for us. The sample function helps us randomly select 100 numbers from the vector 1, 2, 3 all the way to n without replacement. Using the indexes created by this line, we can create the train set and the test set. For the test set, we specify the row number as the indices. For the train set, we specify the row number as all the rows excluding for the indices. Basically, you just need to add a minus sign to tell R that you would like to exclude the rows in the text.index vector. Now, let's do a linear regression, a lasso regression, and a ridge regression. For linear regression, you should use LM function. Key in the formula with your dependent variable or your y variable on the left-hand side, followed by a curly sign. Then, since in this case we would like to include all the 13 independent variables or all the 13 x variables, we can use the full stop sign to represent them. Then, for the data argument, we should specify it as Boston because we refer to all our x and y variables as column names in the Boston dataset. For the lasso regression, we use glmnet function. The first argument is the x variables in the train set. The second argument is the y variable in the train set. Remember, your last column is the y variable or the dependent variable, which is the median value of houses in different suburbs in Boston. The rest of the 13 columns in the Boston dataset is your x variables or independent variables. Note that for glmnet function, the x variables need to be input as a matrix. So I use the s.matrix function to convert the train set from a data frame to a matrix. Alpha is set to 1 for lasso. If you want to run a ridge regression, set alpha to be 0. Family argument is Gaussian because we are doing a regression problem. For a classification problem, family should be specified as something else. Lambda is set as 0.2 for both lasso and ridge. However, lambda value is user-defined, so you can try whatever value you want as long as it is a positive real number. After saving all the results, we can do predictions. In R, we use the predict function to do predictions. Simply input the model name that you have just saved and the x variables in your test set. Here, our x variable is the first 13 columns of the test set. For glmnet model, the x variables need to be input as matrix. So again, I use the s.matrix function. After the prediction, we compute sum of squares of residuals, or SSR in short, with these three lines. Then we can take a look at the three SSRs. As you can see, with lambda equals to 0.2, lasso performs worse than linear model, whereas ridge regression works better than the linear model. However, What about other values of lambda? Is it possible for lasso to work better than linear model if the lambda value is different? As I have talked about in the previous video, we can use cross-validation to determine a good value for lambda. If you have not watched that video and would like to know more about the theory behind cross-validation, you can watch it using the link on the right top corner of the video or in the description below. Now, let's move on to using cross-validation to determine a good lambda value. With GLMNet package, there is a really simple way to carry out cross-validation, the cv.glmnet function. Simply input the x variables, y variable, alpha, and family argument accordingly. Then, R will compute a good lambda value for you. The greatest advantage of cv.glmnet function is that you don't even need to input a range of values for lambda. The function can automatically locate a range of lambda values to test for you. Then you should save the best lambda value as I do here. So basically, you do a cross-validation with the cv.glmnet function and save the best lambda by keying $ and lambda.mean. Then you do a lasso and ridge regression with the entire train set and the best lambda value. After getting an estimate for the lasso and ridge regression, we do predictions and compute SSRs. This time, when you compare the SSRs, you can see that cross-validation indeed helps improve the out-of-sample prediction result of lasso and ridge regression, as both of their SSR values are smaller than when lambda is set at 0.2. In fact, our lasso model now performs better than the linear model.